So problem 2 from your worksheet says a matrix is called symmetric if A transpose equals A. So for a matrix to be symmetric, one, it has to be square, because for two matrices to be equal, they have to be the same size. So only square matrices can be symmetric. Here's a couple examples of some symmetric matrices. 1, 3, 3, 4, 4, 0, 1, 2, 1, 5, 6, 2, 6, 9. There's a couple symmetric matrices, right? All of the off diagonal elements are matched up with each other. Or another way you could say it is this matrix is equal to its own transpose. Right? If this is the matrix A, it is certainly true that A is equal to A transpose. This is the matrix B, it is certainly true that B is equal to B transpose. So then this question that's on your worksheet is to verify that for all 3x3 matrices, that the matrix plus itself plus its transpose is indeed symmetric. So the thing is, how do you do that for all matrices? Well, let me show you for a 2x2 example. So I'm going to show you that for, let's say, any matrix A or all 2x2 matrices, let's call them, have the property. It's really true for any size matrix, but it's easier if you limit yourself to one size. That A plus A transpose is symmetric. There's a couple ways to do this. I think the way that probably what Quran is expecting to see something like to say, okay, well, A can be any 2x2 matrix. So let's say A is the matrix A, B, C, D. Or if you want, you can use the more standard notation A11, A12, A21, A22. Then let's look at A plus A transpose. So here's A transpose. A transpose is going to be, the rows become columns. So this column is going to be a row. So it's going to be AC. And then this column becomes a row. So BD. Or we could use this notation. So then let's look at A plus A transpose. So A plus A transpose is A, B, C, D plus A, C, B, D. When you add those together, you get A plus A, you get B plus C, you get C plus B, which is the same as B plus C, and you get D plus D. And if you look at this matrix is equal to its own transpose. I would probably, if I said this is A plus A transpose, then I would say that the transpose of that is equal to, let's see, the rows become columns. So look, 2A, B plus C, B plus C, 2D. Oh, look, they're equal to each other. But that's exactly what it means for this matrix A plus A transpose to be symmetric, right? It's equal to its own transpose, so it's symmetric. So this is kind of the roadmap for what you want to do for that problem too, except you have to do it for a 3x3 matrix. So your matrix will be like A, B, C, D, E, F, G, H, I, and then you'll do its transpose and you'll add it to itself, and then you'll see that the resulting sum of two matrices is itself a symmetric matrix. It's kind of neat. There are other ways to go about it, but I feel like this is the way you will see the most and learn the most. So I would encourage you to kind of do it that way. All right, let's look at some Leslie matrix steps. So again, hopefully you guys have all checked out the link there. It's just, we're going to go through this kind of, we're going to go through this Leslie matrix handout. So I'm going to read it as well, but if you want to follow along, you certainly can and should. Assuming population is divided into 3 age classes at time equal to 0, where n sub x of t equals the number of females of age x at time t. Okay, so the notation here is maybe a little bit kind of takes a little bit of what's the word for? Takes a little bit of dealing with to kind of get. So here's what we've got. We've got n of t. So this is a vector. Right, that's going to be the number of females of a certain age at time t. So if I want to write the vector for all the females of different ages, I'm going to have the vector consisting of n0 of t, n1 of t, n2 of t. And again, this here is just representing the number of females of age 0. This is the number of females of age, sorry, I should say the number of females of age 0 at time t. The number of females of age 1 at time t, and the number of females of age 2 at time t. Let's make some assumptions. We're going to assume the following. So we're going to assume that 20% of the 0-year-old females survive to age 1, sorry. So 20% of 0-year-olds survive to age 2. This pen is not cutting it anymore. So I'm gonna have to switch to a different color. And then let's also assume, sorry, I set to age 1. So 20% of 0-year-olds survive to age 1. And then we're also assuming 70% of 1-year-olds survive to age 2. And then we'll assume that 0% of 2-year-olds survive. Often when we're modeling something like this, it's like flies and they don't survive, like, or things that have a very short lifespan. So, like, I mean, 2 years is probably long for a fly. Anyway, that's not the point. So we can write some equations if we want. I don't know if they're super necessary, but we could certainly say that we can see that n sub 0 of t plus 1. So the number of 0-year-olds at the next time step is going to be, sorry. See, this is where I'm about to do something different, but this is where the notation can be kind of different. Sorry. The number of 0-year-olds at the next time step we don't know about yet. The number of 1-year-olds at the next time step is going to be 20% of the number of 0-year-olds at the previous time step. And the number of 2-year-olds at the next time step is going to be 70% of the number of 1-year-olds at the previous time step. To me, this looks a little terrible. Let's actually do the diagram thing that she was doing in class on Wednesday, where we say, okay, we can draw these circles and we can say, well, we know how many 0-year-olds become 1-year-olds? Oh, 20% of them. So from here to here, 20%. How many 1-year-olds make to be 2-year-olds? 70% of them. How many 2-year-olds make to be 2-year-olds? I don't even need to draw this arrow because it's a 0, right? You don't need to draw an arrow like that to anywhere if it's 0, because it's kind of assumed. If you don't have an arrow going from somewhere to another place, 0. Let's also talk about how many new 0-year-olds we're going to have. So we're also going to assume that the number of 0-year-olds is the number of offspring from the 1- and 2-year-olds. So let's say 0-year-olds do not make any new 0-year-olds if they're not mature enough. So your 0-year-olds do not produce more 0-year-olds. But 1-year-olds, let's see, what have I got here? 1-year-olds, sorry. 1-year-olds have an average of 3 offspring, so I should say 3 female offspring. So 1-year-olds average 3 female offspring per 1-year-old, and 2-year-olds average, what have I got here? 2 female offspring. We could write it like this. I feel like it's kind of funky, but we could say that the number of 0-year-olds in the next time step, so at time t plus 1, is going to be equal to, well, let's see, how many 0-year-olds are we going to get? We're going to get 3 times the number of 1-year-olds at the previous time step, plus 2 times the number of 2-year-olds at the previous time step. So we're going to get 3 times n1 of t plus 2 times n2 of t. Again, I don't know if these equations are super helpful. They might be. I like this picture personally. So we can see that the number of 0-year-olds is going to be 3 times the number of 1-year-olds plus 2 times the number of 2-year-olds. Okay. So we can make the words. We can make a matrix equation for this. And oh, there was another thing, but we can basically say that, right? So the number of 0-year-olds, 1-year-olds, and 2-year-olds at the next time step is equal to some 3x3 matrix. And this is kind of in the way here. Times the number of 0-year-olds, 1-year-olds, and 2-year-olds at the previous time step. So basically, this is just telling you how to get from one time step to the next step. How many females there are at any particular time step. So I really like what she was saying in class today about how basically, or I actually think some of the students observe this. What you're going to do is what's going in this first row are all the things that are going into the number of 0-year-olds. So how many 0-year-olds are there going to be? Well, I don't get any from themselves, right? There's 0 times the number of 0-year-olds at time t going into the number of 0-year-olds at time t plus 1. But then there's a 3 coming from the 1-year-olds and the 2 coming from the 2-year-olds. Think about it, right? When you do this dotted with this, you get 0 times number of 0-year-olds plus 3 times the number of 1-year-olds plus 2 times the number of 2-year-olds. Okay, how many 1-year-olds are there going to be? Well, the 0-year-olds contribute 20% of their own population to the number of 1-year-olds. So 0.2, and then nothing else is going into there, right? That's the only in arrow, so everything else should be 0. Similarly, for the number of 2-year-olds, the only in arrow is from the number of 1-year-olds. So no 0-year-olds, 0.7 from the 1-year-olds, and nothing from the 0-year-olds. So that is our Leslie matrix, right? The matrix that tells you if you know how many beings of different ages you have at a certain time, you can multiply that by this matrix to see how many you have the next time. And really, this matrix is the same thing we would get if we wrote out this as a matrix equation, right? It's literally, I mean, like, right, if I do the multiplication, this is exactly equal to 3 times n1 plus 2 times n2. And then the second row is going to be 0.2 times n sub 0. And then the third row is going to be 0.7 times n sub 1. Which is exactly these equations here. Okay. So the nice thing about writing it this way is that you can ask how many females there are going to be any number of years later. So if you assume time is measured in years, or I should just say, right, any number of time steps later. So I might want to know, I think I gotta erase this picture. So if we start with, let's see, what do I got here? If we start with 2000 age zeros and 800 age 1 and 200 age 2, how many females are we going to have after 2 iterations of the time step? So if we have this happen twice, well, the easy way to calculate this is to say we're going to have the following. Sorry, that's not what I want to look at. All right, so after 1 year, or after 1 time step, well, we're starting with 2,800, 200. That's our initial. Right, that's how many we have at times 0. Then we're going to multiply that by this matrix that tells us how many we get at the next time interval. Yes, we could totally just use the words that we're giving to us to say, well, like, I know there's going to be 20% of the age 0 ones are going to be age 1, and then 7% of the age 2 ones are going to be age 2. But if you keep doing that over and over again, the calculation you're doing each time gets to be a little bit challenging. So this is going to be, let's see what we get here. 0 times 2,000, 3 times 800, and then 2 times 200. And then the second row is going to be 0.2 times 2,000, which is going to be 400. And then the third row is going to be 0.7 times 800, which is 560. So we get 2,400, 400, and 560. Okay. So that's how many females of age 0, 1, and 2 there will be after 1 time step. After 1 year is what I'm thinking of. Let's do it again. So what about after 2 time steps? So I could say that, right, n sub 0 of 2, n sub 1 of 2, n sub 2 of 2, where 2 is the number of years or time steps. That's just going to be, again, you're going to multiply how many you have after 1 year or 1 time step times the thing that gets you to the next time step. So it's going to be this 0.32, 0.200, 0.70 times this here. So we're going to get something. Let's see. We're going to get 0 times that plus 3 times 400 plus 2 times 560 is going to be, let's see, 1,200 plus 2 times 560. 2 times 560 is 1,120. So 1,200 plus 1,120 is going to be 2,320, I think. Let me double check that. Yep, that's right. And then in the second row, 0.2 times 2,400 is going to be, I made a mistake. That's all right. It's a small mistake. Yeah, thanks. I just was like, that seems wrong. Yeah, that should be 2,800, not 2,400. Good catch, person who sent me the message. Which doesn't affect this part right here. But then for this part here, we get 0.2 times 2,800, which is 560. Purely a coincidence that that's the same as that. And then to get this part here, we get 0.7 times 400, which is going to be 280. So although we're not quite there yet, you might kind of see where we're going with this, which is that if we kept repeating, if we kept asking the question, how many, what's our population of each age group at each next time interval? The question we're kind of looking at asking is, does this have an equilibrium? Is there some number of ages of each age, like age 0, 1, and 2, where if you kept doing this over and over and over again, you would kind of have a limiting value that approached some specific balance of things that were age 0, 1, and 2. So we're kind of gonna be asking the question, does this have an equilibrium? Can we find it? We're a little bit of ways from that, but that is eventually where we're kind of going with this. So let's look at a few more questions just so we can kind of get an idea of how to kind of view these lesson matrices. Again, they're really not that big a deal. They're just kind of, right, like she was saying in class, right? They're just called, they have a name because someone used them and his name was Leslie or her name. Well, I think it was a he, I don't actually remember. So let's look at the following lesson matrix. So here's a lesson matrix. What time is it? I need to keep an eye on the time. Okay. Here's another lesson matrix. And I'm just going to give you these things. So here is the matrix 1, 2.5, 3, 1.5. And then we've got 0.9, 0, 0, 0, 0, 0.3, 0, 0, and then 0, 0, 0.2, 0. So if you look at a matrix, if you look at a lesson matrix like this, after some practice, you can kind of see that when you have a lot of zeros in your rows, it kind of means like, oh, you're kind of thinking about how the ones at a certain age are some percentage of them are getting to the next stage. Let's answer some questions. How many age classes? The number of rows or the number of columns? It's a good question. I mean, I know they're the same, but let's think about it. In the previous matrix, there were 3 age classes, right? There were, I can't think of the right word. There were females. There were females of age 0, age 1, and age 2. And the number of age classes, so rows would be what I would think is at first 2, and you might be right. But here, so here's what I'm seeing. So the vector, right, the matrix, the 3x1 vector that we're multiplying by, that has the number of age categories. But to be able to have this matrix multiplied by that, it had to have, let's see, it's a 3x3 times a 3x1. So it actually is the number of columns that matters, because the number of columns here has to match the number of rows here. So let me put it this way. If it made sense, you could totally have a 4x3 matrix, right? Like I'll just make something up 1, 2, 3, 2, 2, 1, 0, 1, 2, 5, 1, 2 times your 3x1 matrix. Right? If this made sense as a lesson matrix, so I'm not saying it does, but if this made sense, this would still indicate that there were 3 age categories, because we're able to multiply it by the column vector that has 3 age categories and get a meaningful result. And you can do this times this. Now, I'm pretty sure that any lesson matrix is going to be square, so it doesn't really matter. But it is worth noting that it's actually the number of columns that are telling us how many age categories there are. Okay. So, right, we can think of multiplying this by, I don't know, things of age 0, age 1, age 2, age 3. I suppose it only really makes sense to have a square matrix because you can only think of things going into this that are coming from one of the 4 things that are already there. We can also draw the diagram for this, right? We could say, right, things of age 0, age 1, age 2, age 3. Again, it's not going to be a very complicated diagram because let's see. So what's going into N1? Well, so here's the thing, right? What's going into N1, and it's kind of a little bit tricky here. N1's our second thing, right? So if we're saying, right, what's going into N1, we're really asking what's ending up in the second entry here. So I need to do the second row times this column. This row dotted with this column is going to be 0.9 times N0. What's going into N2? Well, N2 is in the third spot down here. It's going to be 0.3 times N1. What's going into N3? It's going to be 0.2 times N2. And again, this is a fairly typical kind of setup where you're saying some percentage of each age group survives to the next age group. And then all of them make babies or make new things at whatever age. Even the ones that are 0 themselves, right? So here we have a 2.5, we have a 3, we have a 1.5, and we also have a 1. That would be our diagram here. Yeah. What else do I want to say about this? I don't know, not a whole lot. So I feel like this lesson matrix stuff, I mean, it's kind of interesting, but so far, there's not a whole lot to it, right? It's like we can say how much stuff makes it from one category to the next category in the next time step that corresponds to writing a matrix, or you can write the matrix and then ask, okay, how can we get the diagram? But so far, that's kind of all we've got. So let me. I think the next 7-ish minutes, because again, I gotta leave early. Probably gonna. I know there's more problems on the handout I sent you guys. You're certainly welcome and encouraged to do them. You can also find the answers to that handout posted on Grant's webpage. Right next to it. So if you go there, you can find it. I can also send you the solutions to the handout if you want it. There they are if you're interested. So if you want more practice with Leslie Matrix stuff, I would encourage you all to take a look at that. But I think in the last few minutes here, I'll say a couple things about what's coming up. So yeah, there's a few special types of matrices / operations that we are really interested in talking about. So one of them is an identity matrix. So an identity matrix is a square matrix with 1s on the diagonal and 0s everywhere else. So the 2x2 identity matrix, which we usually write as capital I sub 2, that's the matrix that looks like this. The 3x3 identity matrix looks like this. And so on, right? The 4x4 identity matrix, okay, it's getting kind of old, right? Okay, so why do we care about identity matrices? Well, they're special. They are the matrix that if you multiply it by any other matrix, you get the other matrix back. So the identity matrix, oh, I always do this thing where I did the thing where I sent I didn't send it to everybody. Apologies. Here is the solutions I was trying to send everybody. There you go. So when I think about an identity matrix, I'm thinking about multiplication. I just think the identity matrix is like the number 1, right? When you multiply 1 by a number, you get the number back. When you multiply an identity matrix by a matrix of the appropriate size, so you do like 1, 0, 0, 0. Sorry, that's not the identity matrix. 1, 0, 0, 1 times, like, say, the matrix 3, 2, 5, 1. You're going to get that matrix back because you're going to get 1, 0 dotted with 3, 5, which is going to give you 3. 1, 0 dotted with 2, 1, which is going to give you 2. 0, 1 dotted with 3, 5, which is going to give you 5. And 0, 1 dotted with 2, 1, which is going to give you 1. Oh, look, we got the same thing back. And it's true whether you multiply on the left or the right, right? Multiply the matrix 3, 2, 5, 1 by the identity matrix 1, 0, 0, 1 like this, you get the same matrix back. So I will mention that most of the time with matrix multiplication, order matters. A times B does not equal B times A in general. But the identity matrix is kind of an exception to that. If you have a square matrix times the identity matrix, it doesn't matter if you do your matrix times the square matrix or the square matrix times your matrix. You get your matrix back either way. Now, if your matrix is not square, the same kind of thing is true, but you have to be a little more careful. So for example, if I say have the 2 by 3 matrix, A equal to, I don't know, my favorite one is the one that's easiest to write out. 1, 2, 3, 4, 5, 6. There is a 2 by 3 matrix. Well, then if you take this matrix and you multiply it by, let's see, I'd have to multiply it by, this is a 2 by 3, so I'd have to multiply it by a 3 by something. So if I multiply it by the 3 by 3 identity matrix, I'll get the matrix back, right? I'll get 1, 2, 3 divided with this is going to be 1. 1, 2, 3 divided with this column is going to be 2. 1, 2, 3 divided with this column is going to be 3. 4, 5, 6 divided with that, right? You're going to get 4, 5, 6. But I just want to mention here that you can't do it the other way around. Right? You can't do this matrix times this matrix like that way because it's not the right size. If you wanted to calculate, if you wanted to do it the other way, you have to do a 2 by 2 identity matrix times the matrix A. And that would also give you back the matrix A. Right? 1, 1, 2, 3, 4, 5, 6. So multiplying by the identity matrix gets you back the matrix that you already started with. The other thing I will mention and then I'll go is this matrix, and I have to remember how to do this. These two matrices have a special relationship with each other. If you multiply them together, at least I think they do, unless they did something stupid. Let's see, 3 times 2 is 6. 5 times -1 is -5, so you get 6 minus 5, which is 1. 3 times -5 plus 5 times 3 is -15 plus 15, which is 0. 1 times 2 plus 2 times -1 is 0. And 1 times -5 plus 2 times 3 is -5 plus 6, which is 1. So these two matrices are called inverses of each other. So if this is A, we call this A inverse. And inverse matrices exactly have the property that when you multiply them together, you get the identity matrix of appropriate size. Only square matrices can have inverse matrices, and not every matrix is invertible. So here's an example. I'm going to pick a real dumb example, a real easy example. This matrix is not invertible because no matter what you multiply it by, you're going to get, let's see, 1 times A plus 3 times C, okay, A plus 3C. 1 times B plus 3 times D, okay, B plus 3D. There's a way I can make that 1 and that 0, but then I'm going to get 0J plus 0C and 0B plus 0D. And no matter what A, B, C, and D are, you're always going to have zeros down here. Meaning this matrix, there is no matrix that is its inverse. It is called not invertible. It's also called singular is the other name for that. So this matrix is definitely invertible, and its inverse is this matrix here. This matrix is not invertible, also known as being singular. And yeah, it doesn't have an inverse. We will definitely talk more about inverses next time. I guess the last thing I'll say, is, and so I should say, we will talk about how to find the inverse of a matrix. Usually in this class, we limit ourselves to finding the inverses of 2 by 2 matrices, which is a very straightforward and pretty easy process. It's possible we might talk about finding the inverse of the 3 by 3 or larger. That process is more involved though. And then the other thing we'll talk about also is how to find the determinant of a matrix. I will just tell you that for this matrix and this matrix, the determinant is 1. So the determinant of a 2 by 2 matrix, find the determinant of any 2 by 2 matrix. It's a different calculation for a larger matrix, for a larger square matrix. It's the product of the diagonal elements, so A times D, minus the product of the off-diagonal elements, B times C. That will definitely be a calculation we use a lot.